Okay, let's go ahead and start. Hi again, for those of you that were here with me last week. For those of you that were not, my name is Leah. I'm very excited to be doing some calculus with you this afternoon. I mostly tutor SAT and ACT prep at Prep Matters, and I teach high school math full-time, a lot of calculus, a lot of statistics, and some IB courses as well. So as a reminder, your microphones are muted. If you have a question, go ahead and type in the Q&A at the top. Try to ask a question through there if you can. If you have longer questions, or if I just don't get to your question in the middle of the session, if you want a more detailed answer, any of those type of things, you are welcome to send an email to classes@prepmatters.com. That email address will be at the bottom of the screen once I start sharing my screen with you. Email that and I will get you as detailed of an answer as I can. Also, as a reminder, for those of you that were here last week, and new information for those of you that are here for the first time today, I'm going to write off of my iPad. So I'm going to turn my camera off so that you're not just staring at the ceiling the entire time, but I'll come back together and talk with us all together at the end of this session as well. So I'm going to go ahead and jump in and start right away so that we can get through as much material as possible. I'm going to go ahead, turn off the camera now, and slightly shift things, hopefully not make too much noise as I do this, but still bear with me if I do. Okay, so let's go ahead and jump right in. This week, we're going to move into contextual application of derivatives, which is the material from units 3 and 4 on the AP Calc syllabus, and most likely was most of your October, maybe early November, if you were in a full year AB class this year during school, maybe a little bit earlier if you were in the AB-BC combo. And as promised last week, we're going to move into actual free response type questions today, with a little bit of skill practice thrown in as well. But before we do that, I want to very quickly review some of the things that I talked about in the last session, some really big ideas that we need to bring through everything that we do in calculus. So remember that the slope of a tangent line, so a line that intersects a function at only one point, gives the instantaneous rate of change. So how a function is actually changing at a specific point in time. That slope of the tangent line, the instantaneous rate of change, those are the same idea. And we know that in calculus as a derivative. The slope of a secant line, or a line that intersects a function at 2 points, gives the average rate of change between 2 points. So just keep that in mind as we go through this. It'll play a part a little bit today, but especially in the next section as we start really thinking through a graphical application of derivatives. Just keep this in mind with everything that we do. We also talked briefly about the ideas of continuity and differentiability. Remember that a function is continuous, so continuous, not necessarily differentiable, but continuous at every point where the limit as x approaches that point exists first, and f of x actually equals that limit. So the limit exists, left side limit equals the right side limit, and the function value is the same number. This means that a function is not continuous anywhere where a left side limit does not equal the right side limit. We usually refer to this as jump discontinuity. The function actually jumps. And a function is also not continuous anywhere where the function value is not equal to the limit. So this is referred to as removable discontinuity. What we're talking about here is some situation where a limit does exist. So the function, the limit as x approaches a point from the left and from the right does exist. That is the same value, but the function value does not equal the same number. This usually looks like a hole on the graph. And a lot of the functions that we work with, smooth functions like polynomial functions, absolute value functions, exponential, logarithmic, radical, sine, cosine, a lot of these functions are continuous everywhere. The big issues are rational functions, functions that have vertical asymptotes and or holes in them, or piecewise functions, so functions that are created by pieces of several different functions. And then one quick thing to just note with differentiability, differentiability is not the same as continuity. A function can be continuous and not necessarily differentiable at all of its points. In order for a function to be differentiable at a point, so we can actually take the derivative, in order for a function to be differentiable at a point, that function needs to be continuous. So continuity is a necessity for differentiability, but it's not automatic that if a function is continuous, it's differentiable at all of the points. Just because a function is continuous at a point, it is not necessarily differentiable. Think about that absolute value function that we talked about in the last session. Remember the connection between a derivative and a slope of a tangent line. If a tangent line with an actual defined slope cannot be drawn at a point, a function is not differentiable at that point. So this happens at points of vertical tangency. So if the slope of the tangent line would be undefined, a vertical tangent line, and sharp edges of a function. So just a very quick visual review of that before we move into new things. If we look at a function that looks like this, for example, so let's say this blue represents f of x, and right here we have the point A. At point A, f of x is absolutely continuous. Limit from the left is equal to the limit from the right. F of A actually equals that limit value. Great. The function is continuous at point A. If I'm tracing the function, I don't need to pick up my pencil at point A. Easy test for continuity. But if I'm drawing a tangent line to my function at point A, my tangent line could look like this. If I'm coming from the left, something like this. Or it could look like this if I'm kind of coming from the right. And those two tangent lines have very different slopes. That's why at this sharp point, sometimes we call this a cusp or a corner in the AP curriculum. At this sharp point, at this sharp turn in the graph, this function is not differentiable. So just keep that in mind as we go through things. A function that is continuous everywhere is not necessarily differentiable everywhere. And this is going to lead us into our first quick skill review today. So we hit on this briefly last time in the first section when we wrote an equation of a line tangent to a function at a particular point. And now we're just going to take this one step further. This is a little bit of a warm up today. Because a curve lies very close to its tangent line near the actual point of tangency, we can use that tangent line to approximate values of a function near that point of tangency. So this word or phrase, local linearity, means exactly that. This means that if we zoom into a function, enough, the actual function, regardless of what type of function it is, will appear linear. It will look like its tangent line at the point of tangency. So I'm not going to be able to zoom in enough to really show you this, but I'm going to try to show you as much as I can here. So if I sketch a function, let's say we draw this function here, and we sketch a tangent line, or as close to a tangent line as I can get right here. So here's my point of tangency. If we zoom in as much as we possibly can, very close to the point of tangency, we'll see local linearity. We'll see that the function appears linear when we're very close to that point of tangency. And what I mean by very close is like this little tiny piece right here, very close. We are as close to a linear pattern as possible right there. That's what local linearity actually means. You may have used the word local linearity in actual class this year. You might have also talked about just linear approximations or tangent line approximations. That's the same thing. That's exactly what I'm talking about right here. So I'm going to walk you through a very quick example. Very quick example of this with some of the easier math, and then talk about conceptually why this would actually help us. Okay, so let's take this away. And let's look at this function here. I have the function f of x equals the square root of x plus 3. A radical function, this is continuous and differentiable everywhere on its domain. So this would have no issues with continuity or differentiability. And if we take the derivative here at this function or of this function, we would end up with, let's go ahead and do that. We would end up with 1/2 times x plus 3 to the negative 1/2 power. And if that's not something that you have done in a long time, if that's not something that you easily remember how to do, easiest way to think through these radical functions is to rewrite them with rational exponents. So instead of the square root of x plus 3, just go ahead and rewrite that as x plus 3 to the 1/2 power. And then we just have a chain rule. Chain rule differentiability, nice and simple. It's just sometimes a little bit easier to recognize with those rational exponents. So now I have my derivative. I'm going to go ahead and write this in the original notation with the square root. It doesn't matter if you want to do that or not. But I know that my derivative now is 1 over the quantity 2 times the square root of x plus 3. Now, in order to do this local linearity situation, to do a linear approximation, I need to pick a point of tangency. I want to figure out what point on the curve I actually care about. So let's use x equals 1 to do this so that we can try to do some quick mental math to really warm up here today. So let's evaluate this derivative at x equals 1. And that would give us 1 over 2 times the square root of 4. So 1 over 2 times 2, and we'll get 1 over 4. I know that my slope of the tangent line at the point x equals 1 equals 1/4. All right, that's background work in order to set up a local linearity problem. Now, I'm going to take this way over here and say, now let's actually go through the steps of a linear approximation. So in order to do a linear approximation, we need that equation of a tangent line. I need to know what the line is that I'm using to approximate. If you can remember from either our last session or if you were not in that one, at some point in your year, we wrote lots of equations of tangent lines. An equation of a line, again, remember that point slope form is the easiest for this. So we use y minus y1 equals m times x minus x sub 1. And in this case, I know that the slope of my line is 1/4. I know that the x value for my line is 1. And I know that I can find the y value at this point of tangency if I take my x value, substitute it into the original equation. So my original equation was f of x equals the square root of x plus 3. Throwing in a 1 for my x, f of x equals the square root of 4. So f of x equals 2. And there's my equation of my tangent line. In the AP curriculum, on the AP exam, we'll generally see this written as an equation solved for y. So y equals 2 plus 1/4 x minus 1. And now we have that equation of the tangent line at x equals 1. Now I can use this to approximate whatever I want, as long as I'm approximating really close to 1. So for example, f of 1.1, or f of 0.95, or f of, that's an ugly approximation sign, sorry, or f of 0.99, something that's really close to the actual value of x equals 1. Again, that local linearity, we're talking about in the actual very close region. Those are not specific math words, but best we can do there. In the very close region of the x value where we built our tangent line, that point of tangency, those are the values that we can make approximations for. All we have to do here is throw in some numbers, throw that into a calculator, get a number. I think what we get here, 2.025. There's your approximation. Now, in this particular case, f of x, our actual original function, that square root of x plus 3, is concave down. So this approximation would be an overestimate. The actual equation of the tangent line is above the function. It's an overestimate, but it's close to the actual function. So that's the actual math of that. Not much more than we did in the first section, just a little bit different wording. But I want to talk through a little bit of theory here before we move on quickly. So in this case, we knew the function. I know that my function is the square root of x plus 3. Doing an approximation doesn't make a lot of sense. If I want to know the actual value of f of 1.1, that's really easy. I'm just going to plug in 1.1. But I could take away this function and instead just tell you that I know that I have a point, 1, 2, on my actual graph of my function, and I know the derivative evaluated at that x value, and just give you that. And then ask you to do a linear approximation using the tangent line for 1.1, for 1.05, for 0.95, for something like that. We don't have to have the function information. In most cases, we don't. So that's a quick skill to start with, using that local linearity idea to do approximations, using that equation of a tangent line to do approximations. In addition to reviewing some of the concepts that we talked about last week, I also want to quickly review some of the skills that we talked about last week, one of which was rewriting an absolute value function using a piecewise function instead. So just very quickly, I had a lot of questions about this one, so I want to make sure that we either remember this or can see this. We have no ability to algebraically find the derivative of something that looks like this. F of x equals 3 times the absolute value of x plus 2. We don't have any derivative rules for absolute value. So in order to algebraically work with an absolute value function, we need to write it as a piecewise function of its two linear pieces. Remember, an absolute value function graphically just makes that v its two pieces of two lines. So we can write this function as the piecewise function that you see here. So in this case, when x is greater than -2, the absolute value of this expression is the exact same value as the actual expression. So when x is greater than -2, we have 3 times the quantity x plus 2. When x is less than -2, we would have to negate our expression in order to have the expression equal its absolute value. So in that case, we have the -3 times x plus 2 quantity when x is less than -2. And if you think through this, this should make a lot of sense with your graphical pieces. We have a negative slope and we have a positive slope to form the actual absolute value graph. Now, when we're doing this, this is a big thing to remember conceptually. When I'm looking at this absolute value function here, when x equals -2, both of these statements are true. If we were truly going to write this out, we would have to pick one of these for the equal to sign. When x is equal to -2, I can use either one of these, but we just need to denote one of them. We can't denote both of them with a sign like this because then we don't have a function, but we do need to use one of them. Now, important thing to really think through here is that I just defined the function in this way. If we were going to take a derivative, we could differentiate both of these to come up with our slopes of our two different tangent lines, but we just need to remember that at x equals -2, that derivative doesn't exist. This function is not differentiable at x equals -2. Even though it is continuous, it is not differentiable. And then we also talked a lot about evaluating limits in the first session. When we're trying to evaluate a limit, the very first thing that we should do is substitute in our values. Try to substitute, see if we can get something that looks nice and pretty that isn't an indeterminate form. And if we can, then great. We evaluated our limit. We know exactly what we're working with. If that first attempt of substitution leads us to something like 0/0, leads us to an indeterminate form, and we're working with polynomials, polynomial over a polynomial, we can try to factor, or we can try to multiply by a variation of 1 using the conjugate. So what I mean by that is something like x minus the square root of 7 over x minus the square root of 7. Some expression that equals the value of 1, the only thing we really could multiply an expression by, but is using the conjugate of either the numerator or the denominator. Those are our kind of quick, short options for working with limits of either polynomial functions or rational functions that are created by a polynomial divided by a polynomial. The easy limits, per se. We also quickly talked about limits at infinity and the relationship between a limit at infinity and a horizontal asymptote, and using our horizontal asymptote rules to evaluate a limit at infinity, or algebraically dividing both numerator and denominator of a rational expression by the term with the highest degree. That works really well when we, again, have a polynomial over a polynomial. It doesn't work all the time, and that's what I'm going to lead us into today. We also talked about a lot recognizing the limit definition of a derivative. So this beautiful looking thing that you see here. If we recognize that as a limit definition of the derivative, that play on the limit as h approaches 0 of f of x plus h minus f of x over h, in this case, kind of switching the x's and the h's, we can see that this expression is actually asking us for the derivative of the function sine of x evaluated at pi over 6. That's if we see this recognition of this limit definition of a derivative. If we don't, and we go through exactly what I just talked about by trying to substitute in first, and we substituted a 0 in for x, we would get sine of pi over 6 minus sine of pi over 6, which is 0, over 0. We get that 0 over 0 indeterminate form. We get that 0 over 0 indeterminate form, and there's nothing algebraically to do with this. We can't factor. There's not a conjugate situation going on. We don't really have anything to do here. This is what's going to lead us right into using L'Hopitals rule. And you can absolutely use that on the last problem that I just talked about, that sine of pi over 6, without recognizing the limit definition of a derivative. This will work as well. So L'Hopitals rule applies when substitution yields an indeterminate form of 0 over 0 or infinity over infinity. So 0 over 0, infinity over infinity. There are other indeterminate forms as well. Those are much more heavily part of the BC curriculum later on. But these are the two indeterminate forms that lead us into the application of L'Hopitals rule. We have to get into a situation that's 0 over 0 or infinity over infinity. Just like we do in these three examples here, almost. Just like we do definitely in the first two examples and with a manipulation on the third. So if we're looking at this right here, the limit as x approaches 1 of natural log of x over x minus 1, if we substitute in 1, natural log of 1 is 0. 1 minus 1, 0. We go right to 0 over 0. If we look at this one, limit as x approaches infinity, we can't necessarily play off our infinity rules here, our horizontal asymptote rules here, because we don't have a polynomial in the numerator. We have a natural log function. So we can think about this not necessarily as substitution, but as thinking through what the functions are doing. The natural log function is strictly increasing. As x increases, the natural log of x increases as well. So as x approaches infinity, the natural log of x will approach infinity as well. And then your denominator, x minus 1, that's a linear function. It has a positive slope. As x approaches infinity, x minus 1 also approaches infinity. I'm at this situation, this indeterminate form where we are dealing with infinity over infinity. And then last situation here, the limit as x approaches negative infinity of x times e to the x. This one is the same as the last one in the idea that substituting doesn't necessarily algebraically make sense. What we're doing looks like we're going to substitute in here, but what we're really doing is thinking about what these two functions are actually doing here. So I have x, I have a linear function, times an exponential function. This linear function, as x approaches negative infinity, this linear function has a positive slope. This linear function is increasing. So as x approaches negative infinity, x is approaching negative infinity. E to the x, however, has a horizontal asymptote at 0. The end behavior of this e to the x function, if we really looked at this like this, as x is approaching negative infinity, e to the x is approaching 0. So we end up with this indeterminate form of negative infinity times 0. This is exactly not what I just said when I said that L'Hopitals rule only works or only can be applied in situations of indeterminate form, 0 over 0 or infinity over infinity, which is not this. But just because we did not get one of those two just mentioned indeterminate forms first right away does not mean that it's not possible. So if I just do a quick rewrite of this function and write it as a fraction using a negative exponent, I will lead myself to one of those indeterminate forms. Because in this case now, as x approaches negative infinity, x approaches negative infinity, and as x approaches negative infinity now in this denominator, this e to the negative x, that will then look like e to the positive infinity. As x approaches infinity, e to the x also approaches infinity. We get this infinity over infinity, negative infinity over positive infinity, that's okay. We get this infinity over infinity indeterminate form. So I did not just give you great notation here. We'll work on this as we actually go through a question. But when we start with our substitution, we end up with one of these two indeterminate forms, 0 over 0 or infinity over infinity. That's when we can apply L'Hopitals rule. And L'Hopitals rule looks like this. L'Hopitals rule tells us that the limit of the quotient of two functions, so the limit of the quotient of two functions is equal to the limit of the quotient of the derivatives of the functions. Notice that this is not at all the chain rule. This is exactly what you're not supposed to do in a chain rule. But when applying L'Hopitals rule, we truly just take the derivative of the numerator, derivative of the denominator separately. That creates a new fraction. Once we do that, we generally have something that then works really beautifully with substitution. L'Hopitals rule can be applied lots of times. But in most cases, it's going to be applied once. You're going to get something that works really nicely with substitution, and you'll be able to evaluate your limit. So for example, if we pop right back up to this one, this by L'Hopitals rule would be equal to 1 over x, which is the derivative of natural log of x, over 1, which is the derivative of x minus 1. Derivative of the numerator, derivative of the denominator. And cleaning that up, just because I know that most of you would never actually go through this step right here. The limit as x approaches 1 of 1 over x. Well, that equals 1 over 1. I'm dropping my limit notation because I actually did the substitution, which equals 1. That's a straightforward usage of L'Hopitals rule. Big key thing to keep in mind here, it's these indeterminate forms that work with L'Hopitals rule, not other indeterminate forms. All right, now we get to go to an AP style question. This question is going to go through 3 different parts. I'm going to go through 3 different parts individually. But altogether, this is a really great AP question because it is almost 100% theory-based. And I think that's really important to note here, really important to think about, because most of us are taking an AP test now in a way that we have never taken a test before. All of a sudden, an AP test has become open notebook, open textbook, open calculator, everything that it was not before, which means that the theory is a lot more important because the theory is something that you're going to have to apply to questions for yourself. You're not necessarily going to be able to find a problem that looks exactly the same in your notes or throw something into a calculator really quickly. You actually have to think and apply things. So this is an incredibly theoretical question here. I love this question. I think it's a great one to look through. And if I were making an open note calculator test, I would model a lot off of this question right here. So anyway, let's look through this question. I have the given information here in the box at the top, and then 3 different parts. A, B, and C. I don't know why I wrote that with a highlighter. Sorry. Parts A, B, and C. So original stem of the question, f and g are twice differentiable functions. That means I can take the first derivative and I can take the second derivative. And f of 3 equals g of 3, which equals 5. So I know that these two functions have the point 3, 5 in common. The line y equals 5 plus 4/3 x minus 3 is tangent to both functions at x equals 3. So this is just a quick manipulation on point slope form. I can see that the point 3, 5 is on this line, and I can see that the slope of this line is 4/3. So automatically from the beginning of this question, I know a lot of things. F and G, I'm going to zoom into this one. F and G are twice differentiable. If they're differentiable, they're also continuous. We just talked about that. For a function to be differentiable, it has to be continuous. Just because it's continuous does not mean it's differentiable everywhere. But if I already know it is differentiable, it has to be continuous. I know that f of 3 equals 5. I know that g of 3 equals 5. But I also know that f prime of 3 equals 4/3. And I also know that g prime of 3 equals 4/3. So I know 4 very helpful pieces of information right there. 1, 2, 3, 4, and this continuity idea before I even got into part A. Now let's jump into just part A here. So part A says another function is given by h of x equals 2x squared f of x over g of x. Find h prime of 3. Now, really, this is just a manipulation of derivative rules. There's not a lot of theory going on in this question, but it is good practice in using some complicated derivative rules and just being really careful with our algebra to get the whole way through this question. So let's step through this. In order to, let's see if I can keep the function on the screen. In order to find the derivative of h of x, and I do want to go through most of this because I want to show you some notational things as we do this. In order to find the derivative of h of x, I need to first apply the quotient rule. The overarching structure of this is the fact that it's a quotient. Within, where did my thing go? Within that quotient, I have a product. So I'm going to deal with these two products, but all together as a quotient. So derivative of a quotient, derivative of the numerator times the denominator. So I'm going to do my denominator here is g of x times the derivative of the numerator. Derivative of the numerator requires a product rule. So 4x times f of x plus 2x squared times f prime of x minus derivative of the denominator times the numerator. And again, you'll be able to write all of your quotient rules, chain rules, everything for you. The memorization part of this is gone. So of course, it's easiest to get through a quotient rule quickly if you know it really well, but it is not the end of the world to remember, especially that order of the numerator, which I know is a very quickly forgotten thing. It's not critical to necessarily have that memorized over other information. And then denominator of the quotient rule is your original denominator squared. So now our h prime of x looks like this, and I want to pause really quickly here because this is one of the notational things that is very often done wrong and is a quick way to lose points. So we know that we are evaluating h prime of 3. And most people have a tendency to just start right away and say h prime of 3 equals blah, 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 with x's everywhere. And that, notation-wise, doesn't make any sense. I did not just write an expression for h prime of 3. I wrote an expression for h prime of x. I wrote an expression for the derivative at any point. We don't want to throw that 3 in there until we actually substitute a 3 in for every single x. And that probably sounds really obvious or hopefully kind of small, but it is something that is looked for when reading an exam. So just be really careful about that. I always like to, even when I'm evaluating at a specific point, to start everything with x's, because for me, it's easier to work through my derivative rules using x's or using that variable. If you are ready to just start right away with a 3, that's fine, but just make sure that every single one of these is a 3, and so on. So you have 3s everywhere. You don't actually have an X anywhere in your expression because you didn't write that out right there. Now, I'm just going to talk through the rest of this. Let's see what I just did here. I have half 3s and half X's. But we are going to evaluate this at 3. So all of our X's become 3s. And look at what we have to know at this point in time. We're going to need to know G of 3. Great, that was in the original information. We're going to need to know F of 3. Great, that was in the original information. We also need to know F prime of 3 and G prime of 3. That's the key from the beginning. That's the key right here, where we associate that derivative with the slope of a tangent line. If we can't remember that the slope of a tangent line is equal to the derivative, we're going to get down to this complicated looking thing and say, well, I have no idea what F prime of 3 is. I have no idea what G prime of 3 is. I can't do anything else. But making that connection there gives you all of your information. Then you're just doing some nice, beautiful algebra. You have a calculator, throw it in a calculator if you want to. I'm going to let you handle that one, but you'll get 108/5. So that's a pretty straightforward question, as long as you can use your derivative rules really well and you're careful with your notation. Don't do what I am in the middle of doing right here, where you have 3 some places and X's other places. Okay, now let's get to the good one. All right, so part B. This is a great question. So part B here, we see that f of x is defined in terms of k of x. F of x equals x squared minus 9 over k of x cubed minus 8. Great, I have no idea what k of x is, so that is incredibly unhelpful at this point in time. We don't know anything about k of x. So let's just see what we do know and see what we can do with this. So this is the key for this question. It is known that the limit as x approaches 3 of f of x can be evaluated using Hopitals Rule. Find k of 3 and k prime of 3. All right, in order to do this, we are absolutely going to have to use limits, since we're being told that Hopitals Rule is going to apply. That's a key that we're being thrown into this limit situation. So let's look at what we know and look at what we can write out here. Okay, so I'm gonna zoom in a little bit, but I'll pull this question right back down. Okay, so I know that the limit as x approaches 3 of f of x, which is k of x cubed minus 8 as a denominator. Sorry, I went through that one backwards. And x squared minus 9 as a numerator. I know that Hopitals Rule applies here. That means that I know that when I substitute in 3, I'm going to get an indeterminate form of 0 over 0 or infinity over infinity. Positive or negative combo there. That's it. That's the option. If Hopitals Rule applies, one of those indeterminate forms is going to result from substituting in a 3. Now, I know that if I'm looking at my numerator, the limit as x approaches 3 of x squared minus 9 equals 3 squared minus 9 equals 0, straight substitution. That therefore means that the limit as x approaches 3 of the denominator of k of x cubed minus 8, all of that is the limit, equals 0. That then tells me that k of 3, substituting in my 3, minus 8 equals 0, or k of 3 cubed equals 8. Did I leave myself any more room to write this? Yes. K of 3 equals 2. So by using this Hopitals Rule situation, knowing that in order for Hopitals Rule to apply, we need to be in an indeterminate form and need to have this substitution yield 0 over 0 or infinity over infinity, because the numerator when 3 is substituted in, will give a 0. The denominator, when 3 is substituted in, also has to give a 0. That's going to lead me to the situation where k of 3 equals 2. Now, that's kind of phase 1 of this question. After I know that, we actually can apply L'Hopital's rule and see what's going to happen. So now we're going to go over here and actually apply L'Hopital's rule. So I'm going to start with the limit as x approaches 3, again, of k of x, I don't know what's happening right here, k of x cubed minus 8 as my denominator. I'm sorry, I always write my denominators first to know how much space I need here. Okay, so the limit as x approaches 3, x squared minus 9 over k of x cubed minus 8, this function that we were already dealing with. I know that this equals the limit as x approaches 3 of 2x divided by 3 k of x squared times k prime of x. And I know that because I applied L'Hopital's rule. So what I have here, what we just looked at, let's see if green will show up here. X squared minus 9, derivative is 2x. K of x cubed minus 8, well, 8 is a constant. It's not going to bring us anything helpful. K of x cubed, that's going to be a chain rule situation. K of x cubed has a derivative of 3 times k of x squared times the derivative of k prime of x. So I applied L'Hopital's rule, got this new limit. Now, I'm going to substitute in here. That equals the, don't want to write that, sorry. That equals 2 times 3, so 6 equals 3 times k of x. Now I know that k of x is 2. No, I don't. Pause. I know that k of 3 is 2, which is what I actually want. K of 3 equals 2. So k of 3 equals 2. 2 squared is 4. So I have a 4 right here. And then I want k prime of 3. That's what this limit is actually equal to. Still not incredibly helpful to me because I'm trying to solve for this k prime of 3, but I have at least simplified the limit. So there's phase 2 of this part. Now, here's the last part. I know that this function, f of x, is differentiable. That was in the question stem. I also know that it's continuous. If something is differentiable, it is continuous. We already talked about that. Because this function is continuous, I know that the limit as x approaches 3 of f of x is going to equal f of 3. That has to be true to make a function continuous. I also already know what f of 3 is. F of 3 is 5. So because this function is continuous, f of 3 is equal to the limit of f of x as x approaches 3, which is equal to 5. And I know that because f of x is differentiable. I almost put that word there. And therefore continuous. Now, last step. That means, therefore, that's going to mean that this limit, where in the world did I just have this? Let's go back to this. 6 over 12, so 1 over 2, k prime of 3. That's going to mean that 1 over 2, k prime of 3, that simplification of the limit that we just evaluated, is going to equal 5. And that will let us solve for k prime of 3, and we'll see that that's 1 over 10. Now, that was a really long question. There's a lot of work in this. In an AP question like this, this is the bulk of the points for this question. If a question is worth 9 points, 9 marks, points in an AP world, sorry, I spent a lot of time in an IB world also, 9 points, then this particular part would be 4, maybe 5 of those. And notice as I just kind of zoom out and sit on this screen right here, there are a lot of words in my answer. There are a lot of words in what we talked about. There's a lot of extra steps in what we talked about. And that's a key for writing out your answers to a free response question. You want to explain everything that you are doing. If you made a jump, if you used a theory, if you used a rule, if you used something, say it. Say that that's what happened. In this case here, we showed that the numerator limit was 0. So then therefore the denominator limit had to be 0 as well. We showed that I used L'Hopitals rule in order to actually jump from this step to this step. Because mathematically, looking at this and then looking at this is not necessarily going to make a lot of sense unless we know that that was a L'Hopital rule application. And then all of this f of 3 equals 5, the limit as x approaches 3 equals 5, this situation, we drew every idea on the fact that f of x is both differentiable and then continuous in order to set this equation. Basically, kind of easiest thing to think about, if you think something in your head to jump from one step to another step in an actual free response question, write it down. Talk about why you are doing it. Are you applying L'Hopital's rule? Great, write that you did that. Are you using the idea that f of x is continuous? Great, write that down. Write down words. Don't be afraid to put words in your answers. Your actual answers do not only have to be numbers. They should not only be numbers. Explain what you're doing. Don't be afraid of using words in order to answer these questions. Okay, now, last part here. This is a super quick part. This would be like a 1-point part here on this actual question. So part C here says, it is known that f of x is less than or equal to g of x for x between 2 and 4, which is great because all of our information tells us that x equals 3. Let m be a function satisfying this statement here, f of x is less than or equal to m of x, which is less than or equal to g of x, again for this x between 2 and 4. Is m continuous at 3? Justify your answer. Okay, so there's two things we have to know about a function in order to answer this continuity question. What is m of 3 and what is the limit as x approaches 3? Do they equal each other? So that's what we want to figure out. So let's go with this statement right here. F of x is less than or equal to m of x, which is less than or equal to g of x. I want to know everything at actual 3, so I don't care about this. And now from the information that we were given, I know that f of 3 is 5, and I know that g of 3 is 5. If m of 3 is between these two identical values, then that means that m of 3 is equal to 5. And this is, if you know these processes or ideas by words, this is the squeeze theorem. Now, we can also do the exact same thing with the limit, or a limit, and say that f of x is less than m of x, which is less than or equal to g of x. If I take the limits as x approaches 3 of f of x, and the limit as x approaches 3 of m of x, and the limit as x approaches 3 of g of x, we can do exactly what we just did with the 5. I know that the limit as x approaches 3 of f of x is equal to 5 because I know that f of x is continuous. I also know that the limit as x approaches 3 of g of x is equal to 5 because g of x is continuous. So I therefore know that the limit as x approaches 3 of m of x equals 5. Now, number one reason that people lose points on a question like this, that is not enough to get credit. That is not answering the question. I know that m of 3 equals 5. I know that the limit as x approaches 3 of m of x equals 5, but I need to show my reader that I know that those two ideas together say that yes, m is continuous at 3. So we need to go one step further. So m of 3 equals 5, and the limit as x approaches 3 of m of x equals 5. So therefore, m is continuous at x equals 5. Nope, not that. Just kidding. At x equals 3. M is continuous at x equals 3. Always double back to the question and make sure you actually explicitly answered the question that you were asked. Not that you did a whole lot of math that led to an answer, but that you tied the pieces together in a nice, pretty bow for your reader, that you answered the question explicitly. All right, let's look at 2 more quick skills before we go back into one last AP problem. First one is finding the derivative of an inverse. Second one is quick implicit differentiation. So finding the derivative of an inverse is, or was, one of the typically most poorly done type questions on an AP exam. And I think that is generally because this formula is very hard to remember. If the formula is not going to be something you need to remember, hopefully these are a little bit easier. But there is often a question about what this number that we're evaluating our derivative actually is. So I do want to run through an example quickly. So what this formula tells us here, let's take away all of my colors. What this formula tells us here is that the derivative of an inverse is equal to the reciprocal of the function's derivative evaluated at an inverse value. So it's kind of a very big play on inverses with having this almost symmetric type formula going on here, but easiest to see when we look at an example. So let's look at this example quickly. Find the derivative of the inverse of f if f of x equals this. So very first thing that I want to do is just find the derivative. Find f prime of x. Again, I'm finding f prime of x, not of 5. I recommend you just always find your derivatives, always find everything in general terms first. So derivative here is, equals 4x plus derivative of tangent is secant squared. This is a chain rule situation. Secant squared of 4 pi x times, not 4 pi, sorry, pi over 4. I don't know what I'm talking about right now. Secant squared of pi over 4x times pi over 4. That's a chain rule right there. Now, that becomes the denominator of our actual inverse formula. So derivative of the inverse evaluated at 5, I'm going to leave that as an x right now, is 4 evaluated at the inverse of x plus pi over 4 secant squared of pi over 4 evaluated at the inverse of x. And that's the big thing to remember there. When that derivative becomes your denominator in this derivative inverse formula, we're not evaluating it at x, we're evaluating it at the inverse of x. Now let's take this away, this x, and let's make this a 5. So x is a 5. That means I need to know the inverse of 5. So quick thing about inverses. Remember that the domain of an inverse is the range of the function. Domain of an inverse is the range of a function. Range of an inverse is the domain of a function. So for example, now totally different function, let's say that h of 2 equals 3. Then I know that the inverse evaluated at 3 equals 2. The domain of a function is the range of the inverse. The range of the function is the domain of the inverse. What's happening here is that these numbers are switching. So in the problem that we are working right now, I need to know what the inverse, what do I need to know? The inverse at 5, which means I need to know what x value in the original function gave me a 5 so that I can do something like this. And now generally this is fairly simple to see when you're looking at an equation. It's either going, or a function, it's either going to be something really straightforward or it's going to be given to you. In this particular case, if we're looking at our function, it's hopefully very easy to see that an x value of 0 will give you a function value of 5, which means that our inverse evaluated at 5 is equal to 0. which means that this is a 0. That is not what I wanted to do, sorry. This is a 0, and this is a 0. That means that when we actually evaluate that, so I'm kind of out, oh yeah, I can do it here. We're gonna go with this. When we evaluate this here, I will have 1 over pi over 4 times secant squared of 0. Secant squared of 0 is 1. Remember that secant is the reciprocal of cosine. So all that I have here is 1 over pi over 4, which is 4 over pi. And that is your quick review of evaluating the derivative of an inverse. All right, last quick skill, implicit differentiation, and then we're going to use this in a related rates problem. So far we've looked at functions that have been expressed by explicitly expressing one variable in terms of another. So f of x equals lots of things with x's. F of a equals lots of things with a. If we move away from the world of functions and think about equations instead, remember that not all equations can be written as functions. So there is a discrepancy between those two words. Then we might not always have the ability to do this, to explicitly represent whatever we're talking about in terms of only one variable. So for example, the equation of a circle is written in terms of x and y. That's what, oh, that is what we have right here. X squared plus y squared equals 16. This is a circle with center at the origin and a radius of 4. If you think about the volume of a box, for instance, that's written in terms of length and width and height. If you think about the volume of a cylinder, that's written in terms of a radius and a height, and so on and so on and so on. We can keep finding equations like this. If we look back to this equation of a circle, we can still find the slope of a tangent line at any point on this circle. We just have to work a little bit harder to get that derivative formula. So turning to implicit differentiation will allow us to find the derivative of y with respect to x, just like we have been doing so far, without writing this x squared plus y squared equals 16 as a function explicitly in terms of y, or in terms of x, sorry. Why would we do that? In terms of x. The key for implicit differentiation, or really kind of any differentiation, is to know what variable we are differentiating with respect to. Derivative of y with respect to x. Derivative of v with respect to t. That variable. What in the world is the variable that we are differentiating with respect to? For every function that we have been looking at, or that you generally look at in the beginning of calculus, you're differentiating with respect to x. That's all you know how to do. When we're doing this implicit differentiation, we can differentiate variables with respect to other variables. So what that looks like is this. I'm going to do a really quick run through of this skill, and then we're going to apply it in an actual question. So just like we can always do in math, we can always do the same thing, that same mathematical process to both sides of an equation. I can multiply both sides of an equation by 2. I can divide both sides of an equation by 17. You can do whatever mathematical operation I want, really, as long as we're doing it to both sides. I can take the natural log of both sides. I can raise both sides to the power of 5, whatever. I can take the derivative of both sides of an equation. So I'm going to take the derivative with respect to x of both sides of an equation. And that would look like this. Now, this can be in parentheses. It doesn't really make a difference. I know that lots of people like to see it in parentheses. Go for it if you want it there. When we look at this left side, this is just a sum or difference rule. Derivative of the sum of x squared plus y squared is equal to the sum of the derivatives of each term. And then this right side, I know that this is 0. I'm just going to keep writing it out for a minute. If you want to turn it into a 0, go for it. Derivative of x squared with respect to x. That's nice and simple. That's what we have been doing. We're taking a derivative of an expression with respect to that actual variable. That's 2x. But the derivative of y squared with respect to x is not just 2y. It is 2y. but then we need to multiply by the derivative of y with respect to x. We are differentiating with respect to x. This was not with respect to x, that was with respect to y. So then we still need to differentiate that y with respect to x. For those of you that are really comfortable with your u substitutions in a chain rule, this is exactly what's happening. And then right side, that equals 0. So then in general, this is usually just taken the whole way down to being solved for the derivative. Kind of depends on what the question is asking you to do. But once we take that derivative with respect to x of both sides and do that implicit differentiation, your goal is then to solve for the derivative, to get an expression for the actual derivative dy over dx. Derivative with respect to x of y is negative x over y. Now I can find my slope of a tangent line at any point of this circle. Those are the quick skills for implicit differentiation. Now we're going to use those quick skills to run through one quick related rates problem, maybe two if I can get this in the amount of time, probably not. So quick related rates problems. I love related rates problems. I feel like my students generally hate them. Actually, I should not even say that I feel like they hate them. I know that they hate them because they tell me this. And I think that one of the reasons that students don't like these type of questions is that because every single related rates question is different. There's not necessarily an easy way to memorize a process because every question setup, every question stem leads you into a little bit of different math. And again, that is why it's so important to think about what you're actually doing, to try to relate your concepts and not just try to memorize a process. It's really hard to memorize a related rates process. So first problem here is an inverted water tank problem. So a water tank is shaped like an inverted circular cone. Let's see if I can make a nice circular cone for you. No. So we have an inverted circular cone. Beautiful. It has a base radius of 3. So I know that my actual dimension of the cone has a radius of 3 and a height of 6. Water is being pumped into the tank at a rate of 2 meters cubed per second. So that's how the volume is changing. Find the rate at which the water level is rising when the water is 4 meters deep. Okay, so we're starting with an empty tank and then the water level is rising. We want to figure out the rate, so derivative, the rate at which the water level is rising. Let's look at the quantities that we are working with here. So try to figure out the variables that we're working with. We have a radius, we have a height, and we have a volume. The actual dimensions of the cone are not going to help us with the actual radius and height of the water per se. I'm not going to just fill in and say r equals 3, h equals 6, great, done, I have this information. We're trying to figure out information about the height of the water, the radius of the water, not the actual tank. So I don't know any of this information right now, but I know that they're all changing. I know that my radius of my water level, I know that my height of my water level, I know that my volume of water is changing. So the radius is changing over time, and the height is changing over time, and the volume is changing over time. And in a related rates problem, it's pretty key that whatever variable you create for yourself, you're also going to have a derivative of that variable. So all that we really know is that this equals 2. And then I'm going to use a particular moment in time to talk about R, H, and V. And that particular moment in time that I'm going to talk about is when H equals 4, I think. Yes, when H equals 4. And my goal is to figure out this. Oh, that was almost good. To figure out this dH over dt. I don't know anything else. So after we pick out all of our quantities, we need to relate the quantities. I need to relate R, H, and V. Easiest way to do that, volume formula. So volume is equal to, for a right circular cone, 1/3 pi r squared h. Again, memorizing formulas is not going to be something that you should really put a ton of complicated kind of thought on right now. Remember that all that volume is the area of the base times height. And then when we're talking about a cone versus a cylinder, we have a scaling factor. Anyway, that will most likely be given to you, or you'll have it in front of you. Once we have this, we need to take the derivative. We need to differentiate this with respect to time. We want to know how things are changing over time. Now, issue with that. When I differentiate this right side, I am going to end up using a product rule because I have two variables, r and h, in one term. When we use a product rule, we're going to end up with an r and an h and a dr over dt and a dh over dt. And we don't know most of those things. So that is going to be incredibly unhelpful to us. In order to make this easier, in order to make this something that actually works for us, we should try to first, before differentiating, write this right side in terms of only one variable. So in terms of r or in terms of h. And in order to do this, in most related rates problems, we turn to geometry. So if we look at our cylinder, and I put my height in my cylinder instead of outside of my cylinder, if I look at the cylinder, when the tank is completely full, I could use this triangle right here, radius of 3, height of 6, to kind of model what's going on. When the cylinder is not completely full, I can still use triangles to model what my water looks like. And every single one of these triangles that I am drawing is a right triangle. And every single one of these triangles that I am drawing has the exact same angle values. All of these triangles that I just drew are similar to each other. And we know that similar triangles are proportional to each other. So I know that, where am I here? I know that at any point in time, the relationship between my height and my radius will follow the same proportion. And I know that that height over that radius, that proportion that we'll work with, is 6 over 3. The height and the radius are proportional to each other in the proportion 6 over 3. Or, in easier words, 2. So I know that h equals to r, or r equals h over 2, whether we're solving for h or we're solving for r. In this case, this is going to be much more helpful to me because I want to differentiate this and end up with a dh over dt in it. So if I do v equals 1/3 pi r squared h, and then just clean that up a little bit. I don't know why I just did that. And clean it up even more. We end up with a formula that's nice and easy to differentiate. I have not actually done any calculus yet. All that I did was write a volume formula, relate r and h using similar triangles, and then write my volume formula in terms of only one variable on the right side. Now I can take the derivative with respect to time, so implicit differentiation, of both sides. When I differentiate this left side, v, derivative of v is 1, but that's with respect to v. So I would need to multiply that 1 by dv over dt. And then I have on this right side, h cubed differentiated is 3h squared, but I need to multiply that by dh over dt. I need to actually take the derivative of h with respect to t. And once we get to this point, once we differentiate both sides of our equation with respect to t, we should be able to substitute in for all but one variable. We should be able to substitute in almost every single thing that we need. And that's exactly what we can do at this point. I know that this is 2. I know that I am evaluating everything at the exact moment that h is 4, and I'm solving for dh over dt. So if we do some very quick kind of math here, I have 12 as a denominator, and then I have 3 times 4. So 2 equals 4 pi times dh over dt. Two over 4 pi equals dh over dt, or 1 over 2 pi equals dh over dt. let's formalize that as dH over dt, the rate of change of the height of the water is 1 over 2 pi meters per, what are we talking about, meters per second? Meters per second. And that is the basic setup of a related rates problem. Basic setup for a related rates problem here looks like this. We always want to try to draw a diagram first. It is very difficult to try to connect all of the different pieces of information that is in a related rates problem just through the words. Once we do that, give symbols to all the quantities that are actually functions of time, relate those with some kind of equation, which is most often a geometry formula. There's also a lot of common related rates problems that use the Pythagorean theorem. If we need to eliminate a variable, we can eliminate a variable. I do want to note that this is not always necessary. Sometimes we will end up with variables, I shouldn't say variables, letters that appear to be variables but that are actually constants. So what I mean by this, so again, I'm talking about this right here, eliminate variables if necessary. If we just did the last problem with the same setup, except instead of a cone, we had a cylinder, the radius of the water level would never be changing. So in that particular case, R would not be a variable, R would be a constant. R would have the same value at all times. We could substitute that value in the beginning right away and be able to just differentiate. Just because something looks like a variable, because we labeled it that way, we said R equals something, doesn't necessarily mean that it is a variable. Think about whether it's changing or not. It might be a constant. Then we can differentiate both sides of the equation with respect to time. Related rates are with respect to time. They use implicit differentiation. Then, easy part, throw in some numbers and solve that there. I'm going to start the next session with a quick review of this with one other type of problem. It looks like this. I'm going to leave this here for a second in case you want to try this later. And this has an answer of 7.8 miles per hour, 7.8. But I'm going to start with that to show you a couple of other tricks and tips here next time. So let me flip back to, as we just quickly review this, note that I did not go through this inverse trig function part right now. I pushed that to a little bit later in the sessions. I promise I will go through it. I'm sorry, I just did not have enough time to go through it in this particular session. It is coming. I will walk you through that, particularly the building the triangle type problems, if that rings a bell to anybody. And I'm going to flip back to not sharing my screen with you and flip back to actually me. And now pretty quickly, I'm going to try to run through some of these questions that I still have unanswered. If you do not have a question, feel free to log off, come back in next Wednesday. Again, look for recordings of these and all of our AP review sessions on the Prep Matters YouTube channel. And again, remember that you can email questions to classes@prepmatters.com for more detailed answers as you need them. So again, if you don't have any questions, feel free to log off. I'm going to see if I can quickly get through some of these. Yes, 3 dots does mean therefore. Good question. 3 dots means therefore. All right, Eric, I see that you figured out your question. And yes, local linearity is a visualization. Let's see how many words I can say at this point in time. Visualization of Euler's method. Good job. We will talk about that a lot more in one of the later BC sessions. So I hope that that answered all of the questions. Again, if you have more questions or think about a question later as you're rewatching something or just want to know something more, please do email that classes@prepmatters.com and I will get back to you with as detailed of an answer as I can. So that is all for this session, and I will look forward to doing calculus with you next week.